It's my pleasure to introduce Rodrigo Moreno, professor of biomedical engineering, who will tell us about synthetic MRI imaging and magnetic resonance. Elastography, please.
Okay, thank you for the invitation, Martina. Yes, so then I prepared this presentation. So actually, my idea at the beginning was to present 3 of our projects, but I think it's too much. So then I think we will have time only to present 2. So let's go for the first one, that is synthetic aging. So this is what we want to do. So then there are like some methods from AI that you just put one picture and then you can generate the aging of this person. So this is included was my PhD student, now a postdoc in my group. And then what we wanted to do is to do the same, but with MRI. So given an MRI, so then get the evolution with time for this person. And then it has like different applications for clinicians. Yes, so then in a way it's kind of the same idea. So given an image, so then generate with AI different images afterwards. So then we went for the literature, and then there's a lot of methods for generative AI for generating synthetic images. So you can see here a lot of people here. None of them are real people. So it is very good methods that are around. Of course, I'm not super interested in this. It is like for fun, but I'm more interested in something that could be useful for clinicians. And so then there are methods that can use the same methods to for medical images. So for example, there are a lot of methods that take, for example, an MRI scan and then generate a synthetic CT scan. And this is actually very useful for clinicians for planning of radiotherapy, for example. In another project with a previous PhD student, we wanted to assess the quality of segmentation of the brain. So then, for example, here you can see a bad segmentation. And then with this segmentation, we can create an MRI that we can subtract from the real MRI and then see that here the segmentation was wrong, for example. Yeah, but then there was a problem. It's very well known that generative AI is not good at anatomy, as you can see. And this is a big problem for us because then if we are working with medical images, if the anatomy is not correct, it's not useful. So then we went back a little bit, and then we said, okay, instead of using this generative AI, we can use deep learning-based registration. So still we use AI, but in the registration frame. And then we need to understand what is this registration. So the concept is kind of simple to understand. Is you have 2 images, and basically you have to align them. That's it. So of course it's more complicated if you ask a computer to do it, but this is the main concept. So you have these 2 images, and then somehow you have to deform to move one to align it to the other one. And then there are many methods, traditional methods that are more complicated or less complicated, depending on what you want to do. In medical images, usually you need to do something that is called diffeomorphic registration, that is a bit more expensive and is very time-consuming, the traditional methods. But the good thing is that for deep learning is fast and accurate. And it's a bit weird that this nonlinear diffeomorphic registration is faster and more accurate for deep learning, but it's more complicated for linear. But yeah, this is something. Yeah. And then we wanted to use this registration frame to generate the synthetic images. The main advantage of that, as I said, is that you guarantee that the image that you are generating are anatomically plausible. Well, this is not the case for the standard generative AI. So we started with, let's say, an easier case is what if you have two images of the same person? So then we can kind of interpolate, let's say, between the two images to fill the blanks. And this is something that is very useful for the clinicians because then they can have one image of the subject and then for some reason the person couldn't come to the following up scan. So then there are a lot of missing data in the database. So you can just fill the blanks with this method. So basically what you do is to do some registration and then you interpolate with this deformation field that I mentioned before. And then the method is very fast because we are just using deep learning for that. And then you can see here, this is one example. One of these images is synthetic and the other is real. So yeah, do you want to make a guess which is which?
Left is synthetic.
Yeah, why? So
Because in the middle, the whole looks a bit sharp, the color.
yeah. Yeah, so it's kind of okay. Oh wait. So of course we are not medical doctors, so we ask a radiologist to check a lot of images, and then his task was to just say synthetic or not synthetic, and then he got it right only in 63% of the cases. So I think it was a very good result. Yes. So, but this is let's say easy because then you need two images, but in the real scenario you just have one image. What to do if you just have one image and then you want to let's say extrapolate from this one image? So it's more complicated. So the idea here was to take this extra information from the population. So what if you can have like a trajectory of a normal person and then use this information to generate this simulation? Or also if you have the same trajectory but for Alzheimer's disease, so then you can simulate different paths depending on what you want to simulate. So, but of course, the first step for that is to have these trajectories of the healthy or AD population. So then we have to like step back a little bit and see what we can do. So in medical imaging, there is like a very common approach that is to use this MRI template. So whenever you want to do like group comparisons, you take your images and then you register to a template that that you use for a comparison of regional differences. And the most used is this MRI template. What is wrong with it, at least for our purpose? So first, it doesn't really look like a person. It's just because then it's, in a way, what they did was just an average of a lot of people. So then, of course, it's very blurred. And then it can affect the accuracy of downstream tests, of course. But then the main problem of MRI is that it's not age result. And that's actually what we want to have, is like to have a template that show you the differences between different like ages. And then use this information to generate the synthetic images. So then we started looking around, and then there was this very good method that uses AI to generate these templates. So you can see the difference, the quality difference here. So this is the MRI. And then, so we had like a loss in the AI to encourage sharpness. So then that's why you can see that it's very sharp. And but the main thing is that you have this age result as well. So this was critical to get it. So once you have that, so then you can create templates at different ages, both for if you use training data from healthy, so then you will have the templates for healthy. If you use the AD for creating the templates, and then you will have the trajectory for AD. So then you can generate a lot of images here, a lot of images here, and then in a way you can then estimate this trajectory that is followed by healthy people or by Alzheimer's people. And then the next step is to use something that, from registration that is called parallel transport, that is to move, let's say, this trajectory into the specific subject that we have. So then it's just to bring, let's say, this trajectory into the space where the subject is. So you can see like a visualization, let's say, of this parallel transport is that here, let's say that is the template, and here you have the subject in this manifold. And then basically you move these deformation fields, so then it fits the space of this subject. Yes, so then this is more or less what we did. And then here is just like a comparison of results. So here we have some publicly available data set. And in this specific case, we had access to 4 time points. It was the same person. So we can compare also the quality of the generation with the actually acquired data. So then these 2 visits is actually the method that I mentioned before. So just taking the first and the last visit and then interpolate. And then these are other methods. And the last one is the one that we just used the templates that I just mentioned. So of course, the 2 visits is, as expected, is the best one because you are using way more information. But just using the templates is not that bad. I think it's very reasonable compared to other methods that also use one image. Yes. So then the next step was, okay, what to do with this? So then there is another field in neuroimaging that is like, there are a lot of papers right now on that, is given an image to estimate the age of the person. And this is called brain age. And then, of course, you can do train a neural network for getting this. It's a regression problem. It's maybe not super difficult to get something working. Actually, this is our method, but there are many other methods. I'm not claiming that this is the best one. But it's just to show that you can do it. And then that was interesting because then right now a lot of people are using this like a biomarker. So if this person has this chronological age, and then you can estimate this brain age, so then you can get this brain gap and use it like a kind of like a biomarker. If it's beyond certain like difference, maybe is a sign of Alzheimer's. But the main modeling of this idea is that Alzheimer's can be seen like an accelerated aging. And our question was, is it true that is the only factor that is determining the Alzheimer's? So then we went on a little bit on this question, and the idea was just to assess if this brain age model is good enough. So then what we did was to reuse our templates that we generated before. And so these are the healthy templates that we created before. And then let's say that you have a subject here. So what we did was to first register this guy to the first image. It's traditionally you use 60 years old because it's like more or less when people start getting Alzheimer's, more or less. So it was a good starting point. And then basically you can have the trajectory, the healthy trajectory with these templates. And then you can, let's say, divide or disentangle the aging from Alzheimer's. You can see this like vector. You can just like use like the component that is following the normal aging, and you have this other component that is more specific for the disease. So if you go, so if this red line, red arrow is 0, so that means that brain age is the only factor that determines Alzheimer's. If you have this red one that is different from 0, that means that there are some other things going on. So then we wanted to see like the importance of this blue and red arrows in every point in the brain. And these are actually the results. So we created a score for the blue one and another score for the red one. So we call it aging score. In a way, it's very similar to brain age. And then the other one is related to this red arrow that I was mentioning before. And then what we found is that here CN means healthy, and then this axis is like the progression of AD, let's say. So the more CDR, the more disease the person is. So what we and we check this in different regions of the brain, and then what we found is that we can find differences just with brain age in all these regions in early stages of Alzheimer's. But if we go for the red arrow, so we didn't find anything here or here, but it was actually visible here. The hippocampus and amygdala that are well known for like being affected by Alzheimer's. So we found differences here when the disease is progressing faster. So then that means that at the beginning, maybe this red arrow is not super important, but at some point it will become more and more important. And it's only affecting the hippocampus and amygdala in this case. So it was interesting finding, I would say. And in a way, what you can think of this AD specific score as a measurement of so maybe this aging score, like more brain age, is more shrinkage of the brain or the cortex or the hippocampus, but here is more like twistings, what you are measuring with this red arrow. So yeah, that was interesting. So still work in progress there, but yeah. Then another project that I just started is okay. Let's assume that we have an AD person. Is it possible to simulate a healthy one from that? So we can have different methods for that. This is just like it was on Monday that we got this image from Felix. So he just used like a normal GAN to generate a healthy image. So it's possible, but I'm not. It's the same as I mentioned before. I was not super happy with, for example, these horns. This is not super anatomically correct, for example. So I would like to test again registration for these purposes. Great. So this is like the first part of the talk. So for the MRI part, so then it's another story. So I can tell you a little bit more about MRI. MRI is a technique that can be used for estimating mechanical properties of the brain. So this is how it works. So then you have your scanner, but it's not enough. You need also like a pump, a pneumatic pump that you connect to a small pillow that is behind your head. And then you're like shaking the head a little bit. And then you use MRI to image this motion of the tissues because of this motion. So this is the raw data you acquire with the scanner, and then with some magic, then you get the stiffness, for example. So then you need the scanner, of course, and you need the pump, but then you need to get synchronization between the scanning and when you put the waves, of course. And the motion is not super. The feeling is more like, I don't know. You haven't been there. It was some other people. The feeling is like these electrical toothbrushes. A little bit more than that, but it's not that dangerous. Let's say. And then, of course, you need to program the MRI to synchronize these motions. And then the next step is to get the stiffness using an inversion algorithm. Yes, and then for this inversion algorithm, this is, I would say, the most difficult part of MRI, is just because you have to solve PDE, that is this Lamé-Navier equation, to get different properties. And you can see here the main property you can get is elasticity and viscosity. And depending on the type of tissue you are interested in, so then viscosity can go down or up. I have a collaboration with Rolly Wang from mechanics, and she's mostly interested in muscles. So it's you can feel. So if you spend your muscle, then it becomes stiffer. So which is a problem for her, because then you have to control that everyone in the scanner is like very relaxed. Otherwise, it's very difficult to compare stiffnesses. But this is something else. But I'm mostly interested in brain tissue. So then usually if you have some problems in your brain, then elasticity goes down and viscosity as well. We have different projects on MRI. So Parkinson's, Alzheimer's, children and adolescents, and multiple sclerosis. And we have also a couple of cases of cancer. These are some results we have, especially for the Parkinson's cohort that we have. Okay. What we found is that age softens the brain. So, and you can see here, this is the age of the subjects, and then this is the stiffness. So then you have this decline here. But then in Parkinson's patients, then this slope is stiffer. It's going down quicker. And then you can see differences in different parts of the brain. So it's very clear that controls have stiffer brains. And we were comparing, we have these two cohorts, the differences. So this is like the mean stiffness of all the health study. and these are the different. So then, and this is in this is also visible in this other view. And of course, this has been reported before as well. There is our colleague Gregoria Carposos from KI. She has now, I think, 80 subjects. See? Oh no, I didn't have that part. Yeah, doesn't matter. So she has found more or less the same thing. So she has both normal aging and AD, and the normal aging, the tissue is softening, and in AD is softening as well, but quicker. And actually, it's very interesting to use MRE for AD just because these differences in stiffness are visible before they are visible in anatomical images. So that's why it's interesting. But something that it was very interesting, I think, is that she also she's a psychologist, so she performed a lot of other psychological tests. One of those was visual memory test. So she just put like some figures, and then you have to remember them. And of course, you get a score from this, let's say, game. And then people with better scores in this game had higher stiffnesses in specific regions in the brain. So it was interesting. So in a way, you can train your brain and get it stiffer. Maybe. Yeah, so that's interesting, but so we know now that stiffness is decreasing with age and disease, but very little is known why. So we thought, okay, we have to have other ways to understand what is happening. So basically what we did was to add a lot of other sequences in our protocols. So we added something that is called multidimensional diffusion. In all studies, QSM, that is something to measure the iron content in the brain. Neuromelanin is also another chemical that is accumulated in Parkinson's disease patients. Diffusion, functional MRI, because is for perfusion, and myelin water imaging is to measure the amount of myelin in the brain. But so far, the most interesting one is this multidimensional diffusion. That we call it MUDI. So there are diffusion MRI. Diffusion MRI is very well known method. So you can get the anisotropy of the tissues in the brain, but this is a little bit more advanced. So it has two parts. The first part is exactly like a typical multi-cell diffusion MRI, but it adds an extra image that is way more complicated, is more sophisticated, and then basically you can excite or take images or information from the whole brain, let's say, at once. So then you can compare these two acquisitions to get more information at the subvoxel level. So I just put these simulations here. So there is something that is mean diffusivity and fractional anisotropy. These two are very commonly used in diffusion MRI. But then with this sequence, you can have something that is the variance of the size, that is called variance of MD, or and also like a micro-FA. So, and then you can see the differences. So here, if you have a low mean diffusivity, that means that the water cannot move that much in the voxel. So then maybe the water is inside the cells. Or here, if it's big, so then that means it is maybe free water, so maybe CSF. But then this is empty. But if you have also the variance, so then here you will have smaller and bigger, more bigger cells maybe, and here you will have a mixture between like cells and free water. So you can distinguish between all these cases. Here for FA, so then in this case, both micro-FA and FA will be high. But here, since there is maybe a crossing of fibers, so then the FA will be low, but still micro-FA will be high. So then we wanted to, and these are just 4 of the parameters you can extract with Moody, but right now we are working with 7. And then basically the idea is to see if we can see what is happening inside the voxel and relate this to the mechanical properties. And these are just like some correlations we found. So we put here stiffness, viscosity, and all the parameters from Moody. And then we added here QSM. It's blurred because some reasons. But yeah, QSM is not really correlated with mechanics, while some of the other parameters of Moody are very much correlated with mechanics. We also found that these correlations depend on the brain, the region of the brain you are. So in some regions, the correlations are higher. In the midbrain, for example, is not so high. So this is actually very interesting because then we can use this as a surrogate of MRI. So because then MRI, the problem is that you have to have this pump, you have to have a complicated setting, but Moody, you don't really need that. So then you can install that in any MRI scanner and get something that is maybe not perfect, but similar to what you could get with MRI. I have another postdoc that is starting working with another idea. The idea is that you have information from Moody about what is happening inside the voxel. And then we have, on the other side, you have the stiffness and viscosity that you get with MRI. So then the question is it possible to get more descriptions of the mechanics that are happening inside the voxel, just using this information from Moody, combining the information from Moody and stiffness that you get from MRI. So then let's say that you have these specific compartments in Moody, so then you can get like micro stiffness or something. This is kind of the idea. And so for that, what we are now doing is that with these Moody parameters, you can simulate different random situations in the voxel and then do some mechanical simulations with FEM and see if you can get something that can be describing what is happening inside the voxel. So this is very preliminary, so we don't really have so many results so far, but that's the idea. Get subvoxel mechanics. For inversion, it's a difficult problem, as I said before. You can use something that is called direct inversion, which makes a lot of assumptions, but is quick. And this is actually what you can get, for example, for the liver. MRI for the liver is actually used in the clinics. It's the only part of the body that is like CE approved. For the brain, is not yet. But if you want to get some more accurate estimations, so then you have to use FEM, which means that it's very, very slow. So the best methods takes 12 hours per subject. So it's not really feasible. But of course, you can also use AI. So this is what we are trying to do as well. So this is one idea. Actually, this is not our work, but it's from another group. So what they did was to have true stiffnesses, simulated ones, and then you can just simulate these wave propagations and use these true stiffnesses as the ground truth. And it works. The problem is that generating these wave simulations from true stiffnesses is already hard if you want to make it accurate. And the other problem is that you are not really using real data. So then it's uncertain if this is modeling what you are getting with the scanner. Another very basic idea that we, of course, tried is just to use, let's say, a unit and then just use inputs and then simulate outputs. It works, but we were not really interested in this, but in just like more the ablation of what happens if you add more information or less information, which is more meaningful for the estimation of stiffness. And we found that FA that I just mentioned from diffusion MRI had like some kind of correlation with the mechanics that was interesting, and that actually this work was before the other one. So then that's why we started like exploring more MODI, if we could explain more what is happening there. Yes, and here this is our current result so far. Is that you can use here this is the, let's say, the estimation of stiffness you can get from the scanner, and this is like what you can get from. This is very preliminary, but this is if you just put as an input all the parameters from MODI. So it's blurred, of course, but we're working on that, work in progress. Yes, but of course this is interesting, but I think there is another way to do it, is to use these pins. And it's very, very interesting for us because then it uses both machine learning and physical models. And this is very useful here because then, of course, we know the equations of the wave propagations. So then we can enforce these physical models into the machine learning. Actually, we did some experiments on that, MRI inversion with pins, and I would say that it works. It's fine. It has some issues, I would say, as well. So the main issue is that as everyone knows, is that you have to retrain for every single subject, which makes it an expensive method. So it's not like a typical AI that you just train once and then for testing is very quick. So no, here you have to retrain every time, and it's time consuming. And another problem is that the geometry of every person is different. So then you cannot really reuse much of the pre-trained networks. But there are, of course, some studies that try to solve these issues. So then we are testing them right now. So it will work at some point, but some issues. So then there is another idea for this is system identification. So the idea is just to learn the PD. Instead of here, you have to put the PD. But what if the quality of the data was bad? So maybe it's not following the PD anymore. So is it possible to learn this PD from the data? And then we can use, okay, if it's following the expected PD, then it's good quality of the data, for example. Or you can even use that as an inversion method. So then how it works is that you have a library of possible components of the governing equation. And then basically what you do is to do some magic to say, okay, these are the most important ones. And then this is actually very similar to what you would expect. So then that means that this is good quality. If you have other components, then you can, okay, what is happening there? And actually, we test this idea with a phantom. So it's a homogeneous phantom, and then we just put, actually, it's like a publicly available phantom. So they put 4 inserts with different stiffnesses. So then this is very high stiffness, and then the others are lower. And then we estimated the components that could of the PDE. And then we found, so if everything is correct, so this Laplacian part should be like the only component that should be active. But and in a way, it's fine for more or less the whole phantom, except for this insert. So we found that it's too dark here. So then we saw that there were some other components that were popping up shear and gradient. So then if you have these two, that means that maybe is this insert was a bit loose. So then maybe it's also shaking and it's creating some kind of artifacts. So that's our hypothesis. So it was interesting to process this way. And now we are trying to use this for the real data, which is way more complicated. That was work in progress. Yeah, so this is more or less what I plan to present today. And yeah, questions.